For lesson 2.8, we will be introducing the idea of limits, and we are going to take some on both continuous and discontinuous functions. Limits are very important to find derivatives, so that's why we're looking at these. So to give a definition, a limit is the value that a function approaches as the input approaches some value. It's not really the best definition. It's a little bit vague. I think this might be something that's better explored through some examples. So let's take a look at these really quick so I can give you some better understanding and terminology here. When taking the limit of a point on the graph, try to imagine the graph as being split up at the particular x value, almost like it's creating a new axis. When we take a limit, we are basically examining what the left and the right sides of the line are doing as they get closer to our point that is directly on the axis. In this situation, we can also say that f of 2 equals 1 because the coordinate 2, 1 exists on the graph. Remember that this is just representative of input and this is representative of output. F of x equals y. So f of 2 equals 1. But we can also say that as we approach the x value of 2 on the left side of the graph, the limit that we approach is 1, and the same for the right side of the graph. Since in both of these situations, as we get closer to the x value of 2 on either side, the y value that the graph appears to be approaching is y equals 1. Thus, we can say that the limit as x approaches 2 of this particular function is 1. When you add these little plus and minus signs as exponents next to the number that you have x approaching, you specifically talk about approaching it from either the left or right side of the point. When you don't use either, what you are talking about is what is typically formally defined as the limit. This might be a little bit confusing because these are also limits, but they're very specific ones. And I don't want to mix people up by saying left side limit, right side limit, and then just limit. So sometimes I use words like true limit or like regular or actual or like formal limit. I'll often use limit for both sides or limit from both sides. So if you hear any terminology like that, it's talking about approaching both sides at the same time. You might think with the left and right side limits why it's even important to have this third thing here, but let's look at another example where the results of the left and right side limits actually have an impact on our true limit here. So here's a graph that looks a lot like the piecewise functions we were looking at in Unit 1. We've got our dividing line right here at x equals 1, so that's where we're going to be evaluating all our limits and points. First off, it should be noted that if we actually wanted to give a y value for this, sort of like we did with the other one with f of 2, we can't here. F of 1 is undefined because neither of these lines have a closed dot. So there's basically no y value for x equals 1 at this point. However, when talking about the limits here, we can give an answer because on the left side of the limit, the line appears to be approaching a y value of positive 2. And on the right side of the limit, the line appears to be approaching a y value of 0. Approaching 1 is 2, and the right side limit of x approaching 1 is 0. What does this mean for the true limit, though? Well, interestingly enough, a true limit cannot exist if the left and right side limits of a particular point do not agree. For our assignment, we'll be doing some more limit evaluations on some functions, both continuous and discontinuous, something that we'll get in a little bit more in the next lesson. But here my prompt says complete the table for the given a values. Now, we usually don't have a anywhere on a graph. This might seem a little bit unfamiliar, but the thing that I notice here is that this has f of a, the limit as x approaches a for all the different limit pieces down here. I think that simply suggests that we're just using this as an input value, and the reason that we're doing that is because there is an x that's already sort of built into the limit formula, and I didn't want to say x approaching some particular x or, use a subscript. It's a little bit easier to just use an a. So know that this is what we're inputting for our x values here. For each of these 4 x values here, we want to find the y value at that point and the left, right, and true limits that go for that x value. Now, what we saw with our above smaller example is if the function doesn't seem to have a break in it, then usually all of these are the same answer. And for every single point on the continuous function here, that is going to be true. The y value at x equals 0 appears to be 4 right here. Therefore, that is the y value of this spot. The y value of 1 appears to be 0. The y value of 2 looks like it's about -4, and the y value of 4 also seems like it is 0. If we draw in our dividing lines here to evaluate the points as limits, we see that our results don't really change. The y value at x equals 0 is 4, and both sides of the line, no matter which direction you're approaching from, also seem to be agreeing with that. Therefore, we can put that for the left and right side, and because these are the same number, our true limit for that is also 4. We're not really going to see any difference with any of these other values. Both of these seem to be approaching 0. Both of these are approaching -4, and both of these are approaching 0. This isn't really supposed to be particularly difficult to accomplish. The point of it is just to show that limits are not anything particularly special when you're just looking at specific values on regular functions. Remember that the true power of this limit is that it can give us the ability to give answers for things that aren't there. So let's look at an example of that with this problem right here. This is another piecewise function, similar to something we might have done in Unit 1, but this has some curve functions in here, so it's a little bit more fun. So drawing in our dividing lines here, we can see we're going to have some different results from the above graph. When we look at our input value of -2, the place where we have a closed circle seems to be at the y value of -1. Even though there is another spot right here, this is an open circle, which means that we're not technically defined at this point. So it would be the correct answer to say here that f of -2 is equal to -1. When it comes to the limits, remember we have the left side of the limit point and the right side of the limit point, which we denote with our negative and positive signs here. On the left side of the limit, the most logical y value that we would get would be attached to this constant line here, which seems to be at y equals 5. So if we were ignoring this entire side of the graph, the most logical answer for this one would be 5. If we were ignoring the left side of this limit, though, then we would be looking at the right side of the graph, which has this parabolic curve right here. And this is what crashed into the original y value that we had of -1. That means that this is going to be our right side limit. Even though the y value and the right side limit agree, the left and right side limits do not particularly agree here. That means that there is no particular limit for the point x equals -2. So we put DNE for does not exist. We can see a similar situation is going to happen over here at 0, where we have a defined y value of 2, a limit on the left side of the graph of another -1, and a limit from the right side of that same 2. Again, because our left and right side limits do not agree here, our true limit does not exist. Looking at this last spot here at x equals 1, we seem to have a defined y value at 3. And it looks like from both the left and right sides of this, even though we have different types of graphs, they are approaching the exact same value. Both of these seem to give y equals 3 as their left and right side limits. Since these limits agree, our true limit is also 3. So that's just a little elementary kind of run through of how to identify a limit on a graph. We're going to end up combining these limits with slopes over time, and eventually that's going to get us to the derivative. But for now, this is sort of just a practice of like looking at where y values are and how those values can be difficult to define depending on whether they are connecting or not. There isn't a Desmos file for this either because it's mostly just a visual activity of identifying points on the graph. Give these a shot, and we will look at some more interesting cases involving limits in our next lesson. Thank you. See you soon.